This is the third and final part of the 8th lesson in heat transfer. The focus of this lesson has been on steady-state, one-dimensional conduction heat transfer in media characterized by constant properties, and in which there is thermal energy generation. In the last part of the lesson, we will continue to discuss the example problem. By the end of this lesson, you should be able to use the particular solution of a differential analysis to calculate the temperature in a medium at any location of interest. You should also be able to use the particular solution of a differential analysis to calculate the rate of conduction heat transfer. On with the lesson. We are working on the example of a planar nuclear fuel element. Due to nuclear decay, thermal energy is generated within the element. We have been motivated by the question, what is the temperature on the inside of the fuel element in steady-state operation? We want to ensure that the fuel element does not overheat to an unsafe temperature. In the second part of the lesson, we developed the particular solution for the temperature distribution within the fuel element. It is shown here for reference. Let's use this particular solution to answer the question for the following given information. The thermal conductivity of the fuel element is taken to be 60 watt per meter Kelvin. Its half thickness is taken to be 15 millimeters. That means that its overall thickness is 3 centimeters. The rate of thermal energy generation within the fuel element due to the conversion of nuclear energy into thermal energy is 2 times 10 to the 7th watts for every cubic meter. Finally, the cooling water on the surface of the element maintains a temperature there of 125 degrees Celsius. The maximum temperature occurs at x equals 0. Substituting x equals 0 into the particular solution gives us the following equation. Here I've substituted in the thermal generation rate, and the thermal conductivity, and the half thickness of the volume. Note that the units do cancel. The watt cancels. The square meter cancels with the meter here to cancel the cubic meter, and we're left over with a degree change unit. The first term is 37.5 degrees C. This is the difference in temperature between the surface and the center line. The center line is 37.5 degrees Celsius higher than the surface temperature, so that the temperature at the center line is 162.5 degrees Celsius. We also may be interested in knowing what is the rate of heat transfer out of the planar fuel element. This energy that is transferred away from the fuel element must be carried away by the cooling flow. There are 2 approaches to answer this question. In the first approach, we used the analysis of the finite control volume conducted in part 1 of this lesson. We applied a finite control volume and showed that the overall rate of thermal energy generation in watts must equal the rate of heat transfer out of the fuel element at the surface by conduction. For one side of the fuel element, we have that the thermal energy generation rate is the volumetric rate times the overall volume. The overall half volume is the area times the half thickness. Substituting values and calculating gives 300,000 watts, or 300 kilowatts. The overall rate of heat transfer is double because there are 2 sides of the element. We can simply take this result and multiply by 2. The overall rate of heat transfer out of the fuel element is 600 kilowatts. The second approach to answering the question is to use the particular solution and apply Fourier's law. The particular solution gives us an equation for the temperature gradient at any location in the fuel element. The temperature gradient is equal to it's negative, and is equal to the thermal energy generation rate divided by the thermal conductivity of the fuel element times the positional coordinate x. Fourier's law allows us to quantify the heat flux given the temperature gradient. Combining these two equations together allows us to calculate the heat flux at the surface of the element. We simply evaluate the temperature gradient at x equal L. This gives that the rate of heat flux at the surface is equal to the volumetric thermal energy generation rate times the half thickness. Multiplying by the area to get the overall heat transfer rate gives us the same result as that which we found from approach number 1. Consequently, we calculate the same rate of heat transfer for one side of the fuel element, and we double that for both sides of the element, so that the overall rate of heat transfer is 600 kilowatts. In this particular example problem of the fuel element, we had a symmetric temperature distribution. We used a symmetry plane and a known surface temperature. These are two examples of boundary conditions that you may encounter in other problems. This slide provides a complete list. There are 4 types of boundary conditions. These boundary conditions are listed in Table 2.2 in your textbook. We have already encountered a known temperature. These boundary conditions are sometimes called Dirichlet boundary conditions. They are noted here, 2 different locations of x. The second type of boundary condition is a known surface heat flux. These are sometimes called Neumann boundary conditions. A non-zero flux means that the flux is specified at some given value at a particular location. Here we have written the known given flux at x equals 0. The flux must equal the conduction heat transfer rate into the medium by applying a surface energy balance at x equals 0. There is also the possibility that the flux is 0. We call this an adiabatic surface. This type of surface exists at any symmetry line. When the flux is equal to 0, from the equation above, it tells us that the temperature gradient at that location must be 0. The third type of boundary condition is convection heat transfer at the surface. This is called a mixed boundary condition. At the surface, for example, x equals 0, we have convection into a fluid on the outside of the solid and conduction on the inside. A surface energy balance reveals that these two heat transfer rates must be equal to one another. That becomes the equation for the boundary condition at the surface. The convection heat transfer rate must equal the conduction heat transfer rate. Because the areas are equal, they cancel, and it works on a flux basis in this particular example. The fourth type of boundary condition is called multi-mode heat transfer. It is another type of mixed boundary condition. Consider, for example, the following problem. Here we have a solid in which there is thermal energy generation. At the surface of this solid, there is an interface between the solid with thermal energy generation, 2 solid materials without thermal energy generation, and over which there is convection heat transfer. Because there is thermal energy generation within the solid to the left, we cannot apply the thermal circuit model. However, in solids A, B, and in the convection, the problem is steady state, one-dimensional, with no thermal energy generation and with constant properties. We are thus allowed to use the thermal circuit to model the heat transfer through this part of the problem. Applying the circuit analogy idea, we draw the circuit for the temperature at the interface, for example at x equal L, to develop an equation for the heat transfer through the solids A, B, and into the fluid. There are 3 resistors: a resistor for conduction in material A, a resistor for conduction in material B, and a resistor for the convection heat transfer, characterized by the temperature difference between the temperature at the interface between the solid with thermal energy generation and the system without, and the fluid temperature. The heat flux is given by the overall temperature difference divided by the total thermal resistance, which is simply the sum of the 3 thermal resistors. The boundary condition equation then becomes that the conduction heat flux at the interface, moving into the interface from the solid with thermal energy generation at x equal L must equal the flux through the system on its surface. As a final note, Appendix C in your textbook tabulates a list of solutions to problems in which the rate of thermal energy generation is a constant. This was the case in the example in Lesson 8. The appendix is to steady-state one-dimensional conduction heat transfer problems with thermal energy generation, what Table 3.3 is for steady-state one-dimensional conduction heat transfer problems without thermal energy generation. You can use it to quickly identify the temperature distribution, heat flux, and heat transfer rate in different geometry systems. If the rate of thermal energy generation is dependent on position, for example as in the case when volumetric absorption of visible radiation occurs in a window, or depends on temperature, which is the case in a chemical reaction, then Appendix C does not apply, and you must evaluate the governing differential equation and solve it. This is the end of the 8th lesson.